Okay, let's get going. Let's get bigger. Okay, so this week we're going to start talking about vectors and matrices. And as we get more into Thursday, we'll be talking about how to do, probability density functions and stuff like that with vectors that contain random variables, particularly the multivariate normal. So we need to be able to understand the notation and whatnot to be able to do that. Also, when you get to implementing your own programs in the Stan language, doing manipulations with vectors and matrices and stuff like that will either be necessary or it will help make your code more general if you can do things like that. So we're going to be going through this. For some of you, it should be review. For others of you, maybe it's the first time that you've seen stuff like this, but either way, we need to learn it before we can get into the more advanced stuff for the rest of the semester. So another thing that we need to review is that you're at Columbia, I'm at Columbia, Stan is at Columbia. You stand around Columbia for business purposes, and according to Columbia's policy, that entails that have to disclose potential conflicts of interest before doing any presentations that basically are about math. So vectors need to learn a slightly different form of math in order to deal with vectors, and we need a little bit of additional notation in order to understand whether we're talking about a vector or whether we're talking about a scalar. And I will follow the reading from the book in that a vector will be written in lowercase boldface like X, and a vector is basically a container of k scalar variables that are written without boldface but in math font. So here we have specifically a column vector X that is of size k. I actually shouldn't say length here. It's of size k. And that can be sort of represented in your head as the vector boldface X as a container for x1, x2, all the way up to the kth scalar x value being contained in the x vector. And so the transpose operator, which is indicated by a superscript T, other books and stuff will use a prime symbol for the transpose operator, which changes a column vector into a row vector and vice versa. So if I write X transpose, I'm thinking about a vector that is oriented horizontally, otherwise known as a row vector. It still contains k scalar elements, but unless I say or indicate otherwise, we're talking about vectors as being oriented vertically, otherwise known as column vectors, rather than row vectors, which are oriented horizontally. But either way, they contain k numbers. Questions about that? No? So there's some differences between how R and Stan handles vectors and matrices and things like that. A lot of the Stan stuff in this regard is inspired more by MATLAB than by R. Anyway, in R, there's not that much of a distinction between a column vector and a row vector. Indeed, everything in R is, or a lot of things in R kind of can be considered a vector. You can have a vector of character strings or, things like that. In Stan specifically, vectors contain real numbers. So that's one difference. And also there's different types between a vector and a row underscore vector that are usually not that important. If you're just, storing stuff, you can store things in either. But if you have to do operations on vectors like matrix or vector multiplication, then it can be more convenient to use one or the other so you don't have to keep transposing things back and forth. R uses the T function to transpose vectors, and later we'll see matrices where instead you should call the transpose function. Although the transpose function is kind of expensive, it has to make a copy. So if you can avoid transposing things back and forth as much as possible, that will make your code run somewhat faster and consume less memory. Yes, Stephanie.
In R, you can make like a column vector of any, so you can't do that instead. It has to be zeros or something like that.
If you just say like vector kx, it's initially initialized to NAs. But then you have to fill it with something that's not NA in order to do anything meaningful.
So if you have an NA left over, will you...
Yes, or another thing with the NA in it. In any event, neither of those are what you want. So you can declare them with NAs, but then you have to put something else into them. Other questions? All right. You know, also with Stan, as we've seen before, when we're writing functions to draw with the prior predictive distribution, you have to declare the vector or whatever it is before you can use it. And when you declare it, you have to say what size it is, even if the size can be passed in from the outside. So you can say vector bracket k bracket to indicate a vector of size k, but k can be specified in your function call or otherwise previously. Okay, so what can we do with vectors? Well, we can define some new probability distributions. These are particularly common in the social sciences. So suppose an outcome can take exactly 1 out of k values per person. So oftentimes on a survey, there'll be a Likert scale or something like that. In this case, we're thinking of sigma as having 3 possibilities: no, maybe, or yes, depending on their opinion to some survey question. And we can represent a yes realization in a number of ways. So we could represent it with the string yes. It's more common in the survey literature, or not the survey literature, but with surveys, to represent this with the number 3. Which is very dangerous because it tends to make people use 3 as if it were, 3 times 1 or something like that. But there's no sense in which yes is triple no or anything like that. So a vector representation of this response would be a vector with first element 0, second element 0, and third element 1. This is known in the engineering literature as one-hot encoding, where you have a vector, all of the elements are 0 except the one that the person responds to. So we can represent this in a number of different ways. If we, anyway, that's our sample space. The categorical distribution is a generalization of the Bernoulli distribution when the sample space has at least 2. And if we're talking about categorical as opposed to Bernoulli, then we think of it as having more than 2 elements that are distinct. They're mutually exclusive, and they span the entire sample space omega. So we can think of a categorical distribution as a generalization of a Bernoulli, and a multinomial distribution as a generalization of the binomial. Binomial, we learned before, can be characterized as the sum of n independent Bernoulli random variables, each with the same scalar probability. So a multinomial distribution is the sum of n categorical distributions, each with the same, that are independent of each other, each with the same probability vector pi. So pi is the parameter to the categorical or the multinomial distribution. It is a vector of non-negative values that sum up to 1. And so the categorical distribution, or the parameter pi of the categorical distribution, is really just representing this probability mass function. You have some probability of being in category 1, some probability of being in category 2, etc., all the way up to some probability of being in category K. These being probabilities, they have to be between 0 and 1. And the sum overall K elements of pi has to be exactly equal to 1. And then we can define the multinomial distribution as the sum of n independent categorical variables that all have the same probability vector pi as their parameter. And this can be represented with the probability mass function n factorial times the product from k equal 1 to k of the probability of falling in the kth category raised to the power the number of times that you see the kth category being realized divided by the factorial of the number of times in the kth category. And the categorical distribution is a special case of the multinomial distribution where n is equal to 1. And consequently, the first term is just 1 factorial or 1. Here, the random variable x transpose is a vector of counts. So each xk element is the number of times that category k is realized, and n tries, and n by construction is equal to the sum of the x's. That is considered given, although you could do some, compositions where n would be a random variable with a Poisson distribution or something like that. And as I said before, pi is a vector also of length k. Its elements are non-negative, and all the elements together sum up to 1. So this is a very common distribution for survey research. Questions about the categorical, the multinomial, pi vector? Okay. So if you were to use the categorical or the multinomial distribution for your likelihood, how would you express your prior beliefs about the pi vector with a PDF? And there is a distribution for that, spelled D-I-R-I-C-H-L-E-T. I've been told in comments that I can't pronounce this correctly, so I won't even try. But it's it seems like it should be French. It's actually German, or the guy is actually German. He's dead, so he's more dead than German. But anyway, it's probably, or something like that. But anyway, it has the following PDF for the pi vector given a vector of parameters, hyperparameters alpha. So it is simply 1 over the multivariate beta function times the product from k equal 1 to k of the kth element of pi raised to the power alpha k minus 1. The hyperparameters alpha are constrained to be non-negative. The multivariate beta function can be written in terms of the gamma function that we're already familiar with. Of course, this distribution, however it's pronounced, is already implemented in R and Stan, so you don't need to literally write out this formula itself. But the gamma function does appear from time to time, and that is implemented in R as the gamma function. In Stan, it's called the T gamma function, which is more of its C++ name. Of course, when doing things in Stan, we're often going to be more interested in the logarithm of the gamma function, which is known as L gamma in the Stan language. In any event, under this distribution, the expectation of a particular value of pi is equal to the ith element of alpha divided by the sum of the alphas. And the mode is going to be alpha I minus 1 divided by -1 plus the sum of the alphas if alpha I is greater than 1. So this is similar to the beta distribution. Indeed, the beta distribution is a special case of this distribution where k is equal to 2, and pi is just equal to pi 1, and the second element is 1 minus pi 1. So a lot of the ways that we think about choosing alpha is the same way we think about choosing the shape parameters of a beta distribution, although there's at least 2 of them, typically more than 2 of them. K is greater than 2 in this case. Just like beta distribution, if all of the shape parameters are equal to 1, then this PDF is going to be constant over the sample, not the sample space, the parameter space theta. And these vectors that are non-negative and add up to 1 are known as simplex vectors. But you can easily see from the definition of the PDF that if all of the alphas are 1, then you're just raising pi to the 0 power, which is just 1, in which case this is just going to be a constant PDF. So you have uniform beliefs about where pi lies in this parameter space, but this parameter space is a closed set. Like with any uniform distribution over a closed set, the maximum entropy distribution is going to be achieved by making it uniform. Also related to the beta distribution, this distribution is conjugate with the multinomial, and so you can do stuff analytically by composing a multinomial likelihood with this distribution for pi. However, if you're doing things like, estimating a multinomial logit regression model, then you're going to be parameterizing pi in terms of a regression function or something like that, in which case you wouldn't be putting this prior on the simplex vector, but rather you'd be putting priors on the coefficients beta in that regression model, in which case you don't have this conjugate relationship, and you would need to use something like stan to estimate the posterior distribution, but you're going to be using stan to estimate the posterior distribution anyway. So the fact that many decades ago Bayesians were doing stuff exploiting the conjugacy of the multinomial likelihood and the Dirichlet prior is sort of a historical artifact. Did I get that about right? No. Tell me how I'm supposed to pronounce that. That sounds pretty much what I said. Same guy, although he had nothing to do with LDA, but it was named after him. It uses this distribution under the hood. Or not, it's not even under the hood. It is explicitly using this distribution. But like the function and topic models, I think it's just setting alpha equal to 1 by default. And so you don't really realize that you're using it as a prior. But that was actually a Bayesian thing. That's why you get a posterior distribution and stuff out of it. Questions other than how to pronounce the dead guy's name? Okay. So matrices. Matrices basically a collection of vectors, or you can think of it as a collection of row vectors that all have the same size, and a matrix is written in capital boldface letters like X here. The first index pertains to the row, the second index pertains to the column. So we can think about a matrix as a collection of K column vectors, or we can equivalently think about a matrix as a collection of P row vectors. So if we just have one subscript on it, this is a little bit ambiguous, but I think the convention most people follow is if you have X that's in boldface, but it has a subscript letter, then this is referring to the Pth column of a larger matrix X, even though that is I said it wrong before. This has k rows and p columns. So it would actually be k row vectors, or we can think of this as a collection of p column vectors. In any event, x in boldface with a subscript p is supposed to indicate the pth column of the larger matrix X. If I write X transpose sub K, I'm referring to the kth row of some larger matrix X. But hopefully it will be clear from the context which referring to. And if I didn't write it up here, but if I just do something like this, X without boldface and have two subscripts, 2 and P, I'm referring to the second row pth column of X. Questions? No? All right. So things that are relatively easy that we'll try to get through quickly. Multiplying or dividing a vector or a matrix by a scalar A is pretty easy. You just multiply or divide each element of that vector or that matrix by A to create a new vector or matrix of the same size. Also easy is adding or subtracting two vectors or matrices that have the same size. So in the case of a matrix, that means it has to have the same number of rows and columns as the matrix you're trying to add or subtract it with in order to have a coherent result. But in that case, you just form a new matrix as the same size, and you just go element by element doing your addition and your subtraction or subtraction. Another thing that trips people up a little bit, but is actually kind of a well-defined thing, is adding or subtracting a scalar to or from a vector or a matrix. And you might say, well, how can you do that if the vector or matrix has multiple elements and a scalar obviously only has one element? But what they're doing when you say like y, the column vector is equal to x, the column vector of the same size, plus the scalar value a, you're implicitly taking a, multiplying it by a vector of ones that has the same size, and now x and this vector, which is just a, have the same size. You can add them together, and that's how y is defined in this case. Obviously, a could be negative, in which case you're really just doing subtraction. So both addition and subtraction for a scalar with a vector or a matrix is considered a well-defined operation. This is also related to R's tendency to recycle A when you're trying to add it to a vector X or something like that. Also easy, perhaps deceptively easy, element-wise multiplication or division of two vectors or two matrices that are all the same size. You just sort of do what you were doing if you did addition and subtraction. You take each element of the container on the left, apply the multiplication or division operator with the corresponding element of the container on the right to form a new vector or a new matrix that has the same size as the two vectors that, or two matrices that you did the element-wise multiplication or division with. In Stan, I think we mentioned this once, but we'll mention it again. These element-wise addition or multiplication and division operators are prefixed with a period, which is oftentimes very difficult to see when you're reading it on a screen with high resolution. Anyway, that's like dot star and dot slash to indicate element-wise multiplication and division respectively. So in Stan, the element-wise operators for multiplication and division have a special symbol, dot star and dot stan or dot slash, and you use the regular star to indicate matrix multiplication, which we'll get to it next. In R, it's actually the other way around. You use the star to indicate either scalar multiplication or element-wise multiplication, and if you want to do matrix multiplication, you have to do a different symbol, parenthesis, what's it called? Percent sign, asterisk, percent sign. So that's a little bit switched the way it's being done in R or with Stan. But in any event, we need separate symbols to distinguish element-wise multiplication from matrix multiplication because they are two very different things. Matrix multiplication actually forms algebra or part of algebra in the strict mathematical sense, whereas element-wise multiplication of two vectors is not really part of the algebra. It's just a convenient thing that sometimes you want to do in context of, you know, some larger function or Stan program. So we'll get to matrix multiplication next. Are there any questions about these more simple operations with vectors, matrices in R or Stan? Still no? Okay. So before we get to vector matrix multiplication, we need to go through vector multiplication. So if x and y are both vectors of size k, then we can define vector multiplication or multiplication of x transpose by y as the sum from k equal 1 to k of the kth element of x multiplied by the kth element of y. So you just take the first element of x multiplied by the first element of y, add it to the second element of x multiplied by the second element of y, etc., summed up over all k values, and the result is a scalar. So vector multiplication inputs two vectors of the same size and outputs a scalar, whereas element-wise multiplication of two vectors inputs two vectors of the same size and outputs a vector of the same size. So you can think of vector multiplication as element-wise multiplication of x and y followed by a summation of your element-wise product between x and y. So you get a scalar out at the end rather than another vector. And this property of vector multiplication is actually very important for defining an algebra in the strict mathematical sense, which we're not really going to get into, but you definitely do need to know the fact that vector multiplication outputs a scalar, and you need to know how to do vector multiplication. Vector multiplication is so important that it has many names, such as dot product, inner product, vector product. Usually if somebody just says product, then they're talking about vector product, and if they really mean element-wise product, they'll say element-wise product. In R, you could do something like T for transpose X multiplied by Y. So here's usage of the percent star percent operator. Equivalently, there's a cross prod function in R, which does the same thing. In Stan, there's actually a dot underscore product function, which in general you want to use. Or if X is already a row vector, then just X star Y will give you the vector product between the row vector X and the column vector Y. Anyway, see both of those being used. A very common construction in statistics is to take one vector and multiply it by its own transpose. So X transpose X, that is going to be defined here. X is taking the place of Y, so we're just doing summation of the squared elements in the container X, getting back a scalar. Stan actually has a special specialization in that operation called the dot self function, which is analogous to the dot product, but it only takes in one vector because we just need the sum of squares for this. In general, and we'll see more about this later in April when we get into the Stan programming in the Stan language a little bit more. Stan has kind of a lot of functions and a lot of functions that do things just slightly differently. So you might say, well, can I just call dot product with x and x if I want, the sum of squares? And the answer is yes, you can. But dot self, which is intended for that purpose, is going to be more efficient because Stan knows the tricks to do auto differentiation with dot self. It doesn't require as much storage in the auto diff process because we just know that the derivative of dot self with respect to x is 2x. Whereas if you call the general dot product with x and y, even if you pass x for both arguments, then it thinks, okay, I need to store the derivatives of x, or the result I need to store the derivatives of this expression with respect to both x and y, but it doesn't know that x and y are the same thing, so it takes up twice as much space in the autodiff process by keeping track of the derivatives with respect to the first argument and the second argument. So if you know that you need a sum of squares, use dot self, and then it knows, oh, okay, I only have to keep track of the derivatives of one vector when doing that. So that is the reason why they have closely related but different functions, and consequently they have different names. Another thing, even though I've been saying it inconsistently, in a mathematical sense, the length of a vector of size k is defined to be the square root of the sum of squares of the elements in X. And this is a little bit confused by R as well as confused previously on the slides, because length X in R actually returns the size of the vector K. So to avoid confusion, it's better to use the nrow function in R. If you use it with all capital letters, it's going to return the number of rows, whether X is a matrix or a vector. But if you use lowercase nrow, that only applies to matrices. In Stan, you can just call the rows function. It will return K, the integer K in this case, the size of X. Similarly, if we're talking about a matrix, there's a cols, C-O-L-S function in Stan that returns the number of columns. Questions about vector multiplication or the functions that you call to do vector multiplication? Any confusion about vector multiplication versus element-wise multiplication of vectors, or other questions? Well, if like we'll see in a little bit when we do a Stan function. So wait.
The length defined as the square root.
That is. It's used with vectors. It's used in matrices. This is the idea of a vector or a matrix norm. It's basically a scalar measure of how big is this vector. So if it has a big sum of squares, in some sense, that is like a bigger vector or a bigger matrix than a smaller vector or a smaller matrix that has the same size. But it's not used that much in statistics. It is sometimes. It's more used in more of a pure math sense. Some things in engineering. Yeah, Sebastian? Yeah. Okay. That's probably a better name. The length thing, they talked about it in the reading. If you take the geometric view of vectors, which we mostly don't, we just take the algebraic view, but you can sort of write a vector emanating from the origin, and this would be like x equal 2, y equal 4, something like that. And then this is a right angle. And so the length of the vector is the hypotenuse. And the hypotenuse, well, in this case, it'd be an equilateral. But in general, it doesn't have to be the hypotenuse there. Okay, the number 1, did you have a question? No. Anybody? Okay. Matrix multiplication is basically a series of vector multiplications. And so obviously with vector multiplication, the two vectors have to be both of the same size, k, in order for this sum of squares thing to make sense. In the case of matrix multiplication, we have an expanded condition as to whether two matrices, x and y, are said to be conformable for multiplication. And that occurs if x is, let's say, a k by m matrix. So it has m columns, and y is a m by p matrix, which is to say it has m rows. Then Z can be defined as the matrix product of x and y. Z is going to be a k by p matrix such that for all of its rows, little k, all of its columns, little p, the element in the kth row and the pth column of the resulting matrix Z is defined as the vector product of the kth row of x with the pth column of y, which is to say it's the sum of the pairs of elements in the xth row or the kth row of x and the pth column of y. Take them, multiply the pairs of elements together, sum it all up. That is a scalar, and that scalar goes in the kth row and the pth column of the resulting matrix Z. You do that for all possible rows x with every column y, all different combinations of that. You can fill up the entire matrix Z with scalars. And so it looks like this. First row, first column of Z is the vector product of the first row of x and the first column of y. Over here, Z2P is the vector product of the second row of x, pth column of y. Finally, in the bottom right, we have the vector product of the kth row of x and the pth column of y. So in order for this to make sense, the number of columns in the matrix on the left here, x, which is m, has to be equal to the number of rows with the matrix on the right in order for there to be the right number of vector multiplications to fill up an entire k by p matrix. And so we say that x and y are conformable for multiplication if the number of columns in x matches the number of rows of y. Otherwise, matrix multiplication between x and y is not defined. But where it is defined, it's just k times p vector multiplications of each row in x, each column of y, and all pairs thereof. So the Z matrix looks like this. Unlike scalar multiplication that you learned in elementary school, matrix multiplication is not commutative. However, it is true that the transpose of the product x and y is equal to y transpose times x transpose. That is always true. I don't know why I wrote i.e. a column vector. That's just false. That's a matrix. I think I was supposed to write that there. So one of the very common constructions we see with matrix multiplication is if you have an n by k so-called design matrix of predictors denoted x, and you have a k by 1 matrix, or i.e. a column vector So a matrix with only one column is basically is a column vector, although it's more efficient in Stan to specifically say it's a vector rather than a k-by-1 matrix. But in any event, if you have an n by k matrix on the left called X and a k-by-1 vector called beta on the right, and you multiply X times beta, you just fill up the resulting vector, which is going to be n by 1, by taking each row of X, vector multiplying it by beta, which stays the same every time. So the first row of X beta is just going to be the sum of each element in the first row of X multiplied by the corresponding element of beta and summed all together to get a so-called linear predictor. Then you do it again for the second row of X and beta all the way down to the nth row of X and beta. We can write this out in terms of scalars with a whole bunch of pluses and pairwise multiplication. In any event, in a generalized linear model, the vector eta is defined as this matrix product between X and beta, and that's why this is known as the linear predictor, because this is a linear matrix algebra operation, and then I can apply some inverse link function element-wise to the elements of eta to map them into the conditional expectation of the outcome given X, like we do in logit models or Poisson models, etc. But if we have like a continuous outcome that we think is conditionally Gaussian, then the inverse link function G can just be the identity function, in which case eta is mu, the conditional mean of the outcome given X. So questions about matrix multiplication, conformability, where it might be used, how it relates to vector multiplication. Any of those? Okay. So matrix multiplication and vector multiplication are really where matrix algebra, linear algebra, differs the most from scalar algebra. And nowhere is that, you know, more apparent by saying, well, only some matrices are even eligible to be multiplied by each other, whereas all scalars can be multiplied by each other. Also, matrix multiplication not being commutative, whereas, you know, one of the fundamental properties of scalar multiplication is that it is commutative. But basically, matrix multiplication is really just a bunch of, you know, scalar operations, particularly scalar products and summation. Does that create any questions? Still no. All right. I think this question came up in the week before spring break. So previously, when you all had been writing Stan functions to draw from the prior predictive distribution, or maybe even just, you know, for the sake of demonstration, writing a function that illustrates the sampling distribution of some frequentist estimator, you had to sort of pass in vector for age and vector for income and other things like that if you wanted to use multiple predictors for, you know, number of retweets or something like that. And I think someone asked, well, how does rstan-arm do what it does, which is to say compile the model on CRAN before it even gets to your computer, and then you can just do y tilde, you know, x1 plus x2, you know, any number of things, interactions, all this stuff, and, you know, it works basically perfectly. And one of the reasons why it does that is that under the hood, the Stan function is expecting a matrix of predictors X rather than, you know, K different vectors of predictors, you know, one for income, one for age, etc. But with k not specified until the user calls stan lm or stan glm or something in the session. When in order to compile this thing, it needs to be known in advance. And so what stan, the way that they're written, is in terms of matrices of predictors rather than a sequence of vectors. And so if I wanted to draw from the prior predictive distribution of a linear model, a better way to do what we've done several times before would be to proceed like this. So I define a function lm underscore rng. It takes an integer s, meaning the number of simulations I want to draw from this prior predictive distribution, matrix X that contains all the predictors that I want to use, and then my other things that I'm passing to this function pertain to the priors, specifically the scale or the standard deviation parameters of the normal priors that I'm using in this particular case. You could use other priors. We talked a little bit before spring break about horseshoe and stuff like that. But in any event, any information that you need to pass to your function to utilize for whatever priors you want can be passed in as arguments to this function. And so I pull out n, which is the number of rows in X. I pull out k, which is the number of columns of X. And then I define the matrix that is going to be returned as out as an n by s matrix. And when you define a matrix, you have to specify both its number of rows and its number of columns. So Stan knows how much space to allocate for it on the heap when this function is called. Consequently, I have to tell Stan that this function is going to be returning a matrix, although here you don't have to specify what the dimensions of it are. Anyway, get those three quantities there, loop over from the first simulation to the last simulation inside the curly braces here. I'm drawing alpha, the intercept, from my normal prior distribution on alpha. So it has an expectation of 0 and a scale or a standard deviation, whatever I pass to it with my function. Then I'm going to draw sigma from my exponential prior on sigma. This is the standard deviation of the errors in a linear model. As we've done before, I like to use the exponential distribution here because it is the maximum entropy distribution for a random variable that is known to be positive. We know what its expectation is, but we're not willing to specify anything more than that in our prior. Exponential distribution has kind of a weird parameterization in that its parameter is a rate, which is the reciprocal of the mean. So what I like to do is just take a draw from the exponential distribution with a rate of 1, which is the same thing as a mean of 1, and then scale it up by whatever sigma scale is. So sigma scale is basically my prior expectation for what sigma, the standard deviation of the errors, is. Then I want to allocate vectors k of size k for beta, my coefficients in a linear model, and a vector of size n for mu, my conditional expectation for y given x. And so as Stephanie was alluding to at the beginning of class today, if I just do vector k beta semicolon, beta is allocated, but at this particular moment, it's just filled with NAs. Same thing for mu. So I have to fill those before I can do anything useful with them or do anything with them that doesn't result in getting another NA, which I don't want. These all have to be declared before I can use them. So in some cases, I can declare and define simultaneously. In other cases, I have to declare and then do something more complicated in order to define the elements of these containers. So in particular, I loop from k equals 1 to k which is the size of beta, filling in the little kth element of beta with a draw from my normal prior on this coefficient. Like most of the times when we specify priors on regression coefficients, it's going to have a prior expectation of 0, some weakly informative standard deviation going into that prior, but because I passed in a vector of scale parameters pertaining to my prior on the betas, I can index that just like I would with R with a bracket, little k bracket. Anyway, that draws from my prior, normal prior distribution on the coefficients for beta. Now that I've filled in beta, it has numbers rather than NAs, and so I can use beta. And I do so on the next line by defining mu, which I previously declared as a vector of size n, as the scalar alpha plus the product of the matrix X and the vector beta. So X is a matrix of size n by k. Beta is a vector of size k. And so n by k, k by 1 results in a vector that's n by 1. I add alpha to each element of that vector, get the resulting vector, which I assign to mu, this being the linear predictor. And in this case, there's no inverse link function. So it is also the conditional expectation of y given x under my priors and the generative model. As you can see here, I'm using in the Stan language star. So star works for both scalar multiplication and matrix multiplication, or multiplication of a matrix and a vector. Here, I don't need to use element-wise multiplication, but if I did, I would have to use the dot star operator. In any event, having now defined mu, I can loop over the n elements of mu, sticking in the lowercase n, lowercase, or nth row s column of my matrix, which I'm going to return when I'm done with all these loops. This is just going to take the conditional expectation of y given x, which is the nth element of mu, add onto it a random draw from the Gaussian distribution for the errors, which is going to have an expectation of 0, and standard deviation sigma, which I had previously drawn from my exponential prior. When that's all done, I have a matrix of size rows n, which is my number of observations, columns s, which is the number of simulations from the prior predictive distribution that I wanted. It's all been filled, whereas at this moment it consists only of NAs. Now I've filled in all the elements of that matrix, and I'm ready to return it at the end. And so this is really what we've done before, but now it can be done for any number of predictors that are all collected together in the design matrix X, rather than having to write a new function for your prior predictive distribution every time your number of predictors changes. This can be compiled once and called many times with different X matrices if you're interested in how the prior predictive distribution changes when you include or exclude another predictor, another interaction, etc. Nathan, number 1.
2 questions. One, so when you use the uppercase letter and the lowercase letter, does it always that means an index of that length of the upper, or is that just like you just did that to make it more clear? Like for example, like lowercase k and capital K. K is the length of whatever it is, integer. It's a value of the length of the column x, of columns, the number of columns of x, but then the lowercase k is the index within k.
Mostly, so Stan has very little ability to infer. So I was really just doing that to be consistent with my math notation. So if I use big scalars like k that are not boldface to usually indicate integers like n and the number of rows, number of columns, etc. And then I will often, although it's not required, if I'm looping over beta, I will use little k when the number of elements is, or the sequence is 1, 2, blah, 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 big K. So yeah, there's nothing magic about any of this. It doesn't tell Stan anything other than what you literally wrote. I was mostly just trying to be consistent in how I write it in math and how I write it in code. Same thing here, defining X is like big X rather than little x to emphasize that this is a matrix. But, it's declared in the function signature as being a matrix. So it's, right there. You had a second question?
Can you just explain a little bit more about beta scale, how you're indexing through, like what it represents? Right.
So I could make beta scale the same value for each of my k coefficients, and each coefficient corresponds to one of my predictors. But I'm also free to use like standard deviation of 0.5 for the first one, standard deviation 3 for the second one, standard deviation 7 for the third one. So I can choose anything I want for those prior standard deviations. I could even choose anything I want for the prior expectations, but convention is strongly in favor of using prior expectation of 0 for regression coefficients, unless it's something that has been, just very well established that, it's not 0. So like price elasticity or something like that, which is almost always going to be negative number for normal goods. In economics, you might put a prior that was not 0 on that. But for most things, we have prior expectation of 0 and some standard deviation. I'm just making it possible that I can pass in a vector of prior standard deviations that correspond to each predictor. So those can be different numbers if I want them to be. So rather than sort of hard coding my priors, I'm giving myself enough flexibility to compile this function once and use it in a lot of situations just by changing, what x is and some of these scales are, rather than changing my code. Other questions? 7, 8?
When you use this, solve it in R and then you apply it, right, to see the distribution?
Yeah, you could make a histogram or a density plot, etc. This is what you think Y will look like before you actually collect data on Y.
And you use that prediction afterwards?
Right. So if you're doing this in RStan ARM, you don't have to write this function. You can just call like stan GLM with prior underscore PD equal true, and it will draw from the prior distribution for all the parameters in your model. And then you can use posterior predict function to get the predictions of Y, even though you're not actually using the posterior to predict, you're only using the prior to predict. But when you use stan GLM by default, it's actually going to condition on the outcome. That way you get posterior draws of the parameters, and then you can get posterior predictions. But this is really more an exercise in trying to understand the Stan language. And, let's say before you even have the actual data that you want to use, you're maybe pre-registering or something like that. You want to think about, well, what priors should I be using? What prior scales to these normal distributions should I be using? You can write yourself a function like this in the Stan language, expose it to R, call it, play around with different values of alpha scale, different values of beta scale, different values of sigma scale, different predictors in the matrix X, until you get, predictions of the outcome Y that look somewhat reasonable, and then you might, pre-register those or a sequence of those, things like that. So all the reasons why the prior predicted distribution is an important part of the Bayesian workflow imply we need a way, whether it's for this model or some other model, to draw from the prior predicted distribution in order to understand the implications of our priors, particularly if in the end we want to use posterior probabilities on models to say it's more likely that one model is true than another model is true, conditional on the event that one of the models that we're estimating is true, which we talked about a little bit on Thursday before spring break. If you're going to do that, then it is really important that you think about your priors and presumably pre-register your priors in advance, because really that exercise is more just a contest to see which model has the best priors associated with it, in the sense that the data that you then give to these functions looks more like one prior predictive distribution than another prior predictive distribution. Jonathan, you had a question?
Yeah, so the alpha, that also refers to prior beliefs right there?
Yes. So this is the intercept in a linear model,
Sure.
and we have prior beliefs about all the unknowns,
Okay.
including the intercept. Here, certainly a case could be made for using a non-zero prior expectation, particularly if the columns of X are centered, which they basically always should be. It gives you a free, easy way to get a better interpretation of alpha as the expectation of Y for the average X, but that's not quite, but pretty close to the unconditional expectation of Y, which you should have some intuition about even before you go to collect new data. And so you can set alpha to be centered on what you believe Y to be conditionally on the average X or unconditional. So leave.
Also, question is related to question before, but like if in the matrix, for instance, one of the columns there's a missing value, will that basically just like the type function drop that observation, and will it adjust out the length of the size of the matrix?
Right. So if you are using RStan ARM, it will by default drop any rows that have missing this on X before it gets started. And so the X that gets passed to Stan doesn't have any NAs in it because those rows already got dropped. Here, I'm also implicitly assuming the X's don't have any NAs in them. If they did, you would actually get an error message. Pretty sure. So Stan doesn't really, unlike R, Stan doesn't let you pass NA values from R to Stan. You can, use NAs in the Stan language. So right at this moment, beta is initiated to all NAs, but you can't really give it NAs from the outside. Other questions? All right, rolling along. There are a variety of matrices that have special names or special adjectives associated with them. So one is a square matrix. That is a matrix that has the same number of rows as it has columns. A square matrix X is said to be symmetric if and only if it is equal to its own transpose. So the transpose of a matrix switches the column and row indices of the scalars contained in that matrix. And if it happens to be the case that X is equal to its own transpose, we say that the matrix is symmetric. So that's going to entail that the X12 element is equal to the X21 element, and the X34 element is equal to the X43 element for the entire X matrix. If that holds for all elements, then X is said to be symmetric. Triangular matrices are a special kind of square matrix that have zeros in one corner or another. So a lower triangular square matrix X is going to have zeros anytime the column index is greater than the row index. So a lower triangular matrix is going to have zeros in its top right corner. It can have anything along the diagonal. It can have anything below the diagonal, but a lower triangular matrix has to have zeros in its upper right corner. Conversely, a upper triangular square matrix is going to have zeros whenever the row index is greater than the column index. So it's going to have zeros in its lower left corner. Anything on the diagonal anything in the upper right corner, but it has to have zeros in the lower left corner. A diagonal matrix is a square matrix that is both lower triangular and upper triangular. So it has zeros everywhere except along the diagonal. It can have zeros some along the diagonal as well, but the diagonal is free, whereas in the triangle, for the lower triangle and the upper triangle, it has to be 0. So it's going to be 0 whenever the column index differs from the row index. Identity matrix, special kind of diagonal matrix that has all ones along its diagonal. So I of KP is going to be 1 along the diagonal, 0 in the off diagonal. This is the matrix analog of the scalar number 1. A matrix that is not the identity matrix but has ones throughout is often known as a ones matrix, but it is not analogous to the scalar number 1. The identity matrix is analogous to the scalar number 1. The identity matrix is special and called the identity matrix because if X is square, or even if it's not, as long as it's conformable for multiplication with the identity matrix, X times I is equal to X. And that's what makes the identity matrix the identity matrix. That's what makes it analogous to the scalar number 1. And also I times X is equal to X if I and X are conformable for multiplication the other way. Another type of special matrix is known as the orthogonal matrix. And our orthogonal matrix Q is one such that Q transpose times Q is equal to the identity matrix. It can also be shown that Q times Q transpose is equal to the identity matrix. But in general, Q transpose, matrix transpose times matrix is not equal to matrix times matrix transpose. That is a special property of orthogonal matrices. And moreover, orthogonal matrices, the product of it in its own transpose is an identity matrix. Questions about any of that vocabulary? Okay. One particular type of product, which is really just a special case of regular matrix multiplication, but we might as well talk about it separately, is the product involving a diagonal matrix, D, and some matrix X. So if I multiply D on the left, X on the right, presuming that these are conformable for multiplication, the result looks like this. So we take each row of X, scale it up by the corresponding diagonal element of D to form a new matrix, which is just D11 times this row vector, D22 times the second row vector, etc., all the way down. And so taking a diagonal matrix, multiplying it on the right by some matrix X, scales each row of X by the corresponding diagonal element of D. Conversely, if we take some matrix X, multiply it on the right by a diagonal matrix D, then we look at things column-wise like this. Each column of the matrix on the left, X, is being scaled up by the corresponding diagonal element of D. So we get first column of X multiplied by D11, second column of X multiplied by D22, last column of X multiplied by DKK. And consequently, you can see that if D is actually the identity matrix, then all of these are ones, all of those are ones. And you're just scaling by 1. Consequently, identity matrix times X is just going to be X. And X times identity matrix, again, just X. So as long as these are conformable for multiplication, diagonal product is just sort of either scaling up the rows or scaling up the columns of the matrix it's being multiplied with. Questions? Okay, inverse of a matrix. this is another thing that makes matrix algebra different from scalar algebra. So if X is a square matrix, which is to say it has k rows, k columns, then the inverse of X, provided it exists, which it typically will for a square matrix, is denoted X superscript -1. And if it exists, it's the unique matrix. It's also a square matrix such that X times the inverse of X is equal to the identity matrix. And also the inverse of X times X also equal to the identity matrix, because those are both going to be conformable for multiplication. Now, you don't really have to worry about how software like R and Stan finds the elements of X inverse. It's not too difficult to do if X is diagonal. It's also not too difficult to do if X is triangular. It's not difficult to do in general, provided that you're doing this with a computer rather than by hand. It can be very tedious to do by hand, but you just call a function on a computer and it does it for you. So there's really no such thing as vector or matrix division, but there is such a thing as multiplying X or any matrix really by the inverse of X. And that's kind of like division is in the scalar sense, because you can take A, multiply it by the reciprocal of A, and you're going to get 1 provided that A is not 0. And so if you take X and you multiply it by the inverse of X, you get the identity matrix, which is the analog of the matrix number 1, provided that the inverse of X exists, which is sort of the same way as saying provided that A is not 0 here. Also, matrix times scalar inverse is equal to reciprocal of scalar times matrix inverse. Another couple properties that you should remember: the inverse of a product is equal to the product of the inverses, but in reverse order. So XY quantity inverse is equal to Y inverse X inverse. And the inverse of a transpose is equal to the transpose of the inverse. So this identity. Anyway, should understand this idea of matrix inverse, and quickly we'll show one way in which matrix inverse is being used. So in Stan, or in R-Stan-Arm, I said, well, if you're not going to use informative priors on your coefficients, you should specify QR equal true. And what does that do? So if we let the vector of the linear predictors in a generalized linear model be, X times beta, the matrix product there, it's true that any matrix, such as X, can be written as the product of an orthogonal matrix and an upper triangular matrix. Indeed, this is called the QR decomposition, because Q for orthogonal, R for upper triangular. And it's unique if you take the diagonal elements of R to be non-negative. And we can always make that so just by multiplying some stuff by -1. So we're going to use the QR representation of X. And so if eta is equal to X times beta, we can write that as eta is equal to Q times R times beta. Or we can write that as equal to Q times theta, where theta is equal to R times beta, just by using properties of matrix algebra. And so when you specify QR equal true, what R-Stan-Arm is doing, without you necessarily knowing it, it's doing a GLM of your outcome using Q as the matrix of predictors rather than X, in order to get the posterior distribution of theta, which is the coefficients on Q. But before returning it, it pre-multiplies each draw of theta by the inverse of R in order to get a posterior draw of beta, which is equal to R inverse times theta. So if theta is defined as R times beta, and we multiply by R inverse times R is the identity matrix times beta is beta, and thus we're getting posterior draws of beta from posterior draws of theta. And then when it's returned to you, all you see is the betas and like the alpha and the sigma. You don't see anything about theta. So why go through all that? Well, doing so makes it a lot easier for nuts to sample from the posterior distribution of theta, because the columns of Q are orthogonal to each other. You multiply one column of Q by another column of Q, you get 0. That's what it means for two vectors to be orthogonal. Consequently, there's much less dependence of one element of theta with another element of theta, and that makes it really easy for Stan to draw from the posterior distribution of theta very efficiently. There's tends to be no divergences. It converges quickly. You get a high effective sample size. All these good things, and then you multiply it by R inverse internally to get posterior draws of beta, which are the coefficients on X, and it looks like to the user that you were getting the posterior distribution of beta directly all along. But really, you were doing it with a transformation and an untransformation internally to enhance the sampling efficiency of the MCMC algorithm in Stan. So the only thing that's weird about it is that when you specify the priors, you're actually specifying them on theta, and who really knows what reasonable priors on theta would be. But if you're going to use the default ones, they apply to theta just as well as they apply to theta. And so you can specify QR equal true to get better effective sample size and to avoid a lot of the problems, particularly if you have like age and age squared or something like that in your model, which are going to be very highly correlated with each other, makes it harder to draw, from the coefficient on age and age squared at the same time. Okay, that's all for today. Pick it up on Thursday. Talk about some more matrix algebra stuff. Talk about the multivariate normal distribution, which is by far the most important multivariate probability distribution that we'll be using, and draw out some implications of using that multivariate normal for all kinds of things.